So good morning all of you. So I have got it confirmed from one of your classmates that I am audible and the screen is visible. So we will start from the point where we left in the last lecture. Today our aim is to at least complete DPCM and study the T1 system. So that in the last lecture on Friday, we should do the gram split procedure. Okay, so I plan to do it first, and then after mid-sem we will try to introduce the signal space in a better manner. So we'll try to complete these three topics in the two classes, that is today and on Friday, and this would form the course for mid-sem. And there was a question regarding the pattern of the exam. See, it is very simple. Few objective questions and few subjective questions. And objective questions you may need to solve in rough and just take the right answer. And for the subjective question, you need not to write in all the steps. You just need to feed in, let us say, 4 intermediate steps. For example, if you solve something, you simply can write after solving this equation, I get P as this. So then you can write using this P, I obtain another parameter like this. So a simple way to answer. So only those two type of questions mostly should be there. But before finalizing anything, I need to talk to Professor Durkhamkar because he is taking section B. But this is what I can think of, that half objective, half subjective, and maybe few fill in the blanks. This is the possibility. If at all there is any change, we will let you know definitely on Friday, because we both instructors need to meet for this first. So we will definitely have a meeting in the days ahead. So we were discussing DPCM. So for DPCM, we basically built our base by saying that the speech signal is generally is not having a high frequency component. It's a slowly varying signal, and because of its slowly varying nature, that is, we saw it from the autocorrelation as well as from the PST. So we can basically transmit the difference between successive samples. Okay, m of k minus m of k minus 1. So that is the motivation because of the above two phenomena, which must have been observed by the designers after evaluating several thousands of speech samples. Okay. So we found out that D of k will definitely be much less than m of k. That is quite obvious. That we showed that if it is the current sample is 5, the next sample is 5.2, so definitely it should be 0.2. Why I am saying 5.2? Because the signal is slowly varying. This may be 5.01 as well, because this depends upon our sampling rate. So why sampling rate? Because sampling rate decides the gap between the two samples in time. Okay. So we said that at the receiver, knowing dk and several previous values, we can reconstruct m of k. Now, what is the benefit of doing this? So this is what is very important. This is the difference between successive samples is generally much smaller than the sample values. So the MP, that is the, you can say, the minimum and the maximum amplitude which your quantizer takes in, will definitely reduce. Once it reduces, you know that delta V, that is a step size, or you can say, I think step length, whatever word you must have used in earlier lectures, that will decrease. And because of this decrease, your quantization noise will decrease. So once your quantization noise decreases, your SQNR will improve. Okay. Another thing is, so this is for a given L. It means we have fixed the number of quantization levels L. Okay, so it means your bit number of bits will remain same, but SQNR will improve. Another thing is that it implies for a given n we can increase the SNR, or for a given SQNR we can reduce it. It means that if you are satisfied with the level of SQNR, then you can decrease the number of quantization levels. Now, why this is also beneficial? Because it will reduce the bandwidth consumption. Why? Because your n reduces. If you are using 4 bits to quantize or encode one sample, then you are using 3 bits. So 3 bits you can have a far wider pulse width. Okay. And we have seen that the narrower is the pulse, the higher is the bandwidth consumption. This you can directly relate from the Fourier transform of rect and sinc. Okay, if you do not remember earlier lectures. So we closed our lecture with this, that now can we increase this benefit further? If people observe that if really the signal is slowly varying, if it is, you can say, possesses a lot of derivatives, or you can say it's smooth function, the category of smooth functions. So why not predict the current sample based on the previous samples? If we can do that and our prediction is worth enough, then this m of k minus the predicted value of the sample would be definitely smaller than this d of k, will be further smaller. Now, why are we doing this? Is because there are several reasons. One is that increasing SQ9 is always better because its quantization noise is somewhat which we cannot recover. It means we cannot remove it completely at the receiver. And secondly, if at all we can decrease the bandwidth consumption, that is also great. We will see in P1 system that we want to multiplex several voice signals as well. It means that, let us say, if in your area you have 300 telephones, so it should not be that 300 wires are being carried from that area to the telephone exchange. So this multiplexing helps these all 300 telephones to be deployed on a single wire. Okay, and for that, decreasing N is also a very good thing to do. Okay, means it will help you deploy those 300 telephones together. Okay, so let us start with today's class. Okay, so we will complete DPC today. So I'm directly starting from the point where we left. So if our prediction is worth enough means that the samples are close by, that is, whatever it predicts is really close to the original sample. Predicted value m cap k, let us say m cap k is what is predicted, will be close to m k. Okay, will be close to m of k, and their difference that is prediction error will be even smaller than the difference between the successive samples. Okay, so this is the motivation. I just written it for the sake of completion so that in the notes things are complete. So this scheme is called DPC. Okay, this scheme, the above scheme, is called DPCM, that is differential pulse mode modulation. The differential word now should be very clear. That why? Because we are taking difference of either we are doing mk minus 1, or we are doing mk minus n cap k. Okay, and then we are using pulse code modulation over it. We are quantizing the difference and then we are encoding it. So the process is same that of PCM. So this DPCM word comes from there. Okay. Now we will do the motivation of prediction. Let us say the signal is, so consider, this is just to motivate. Okay, consider, for example, a signal MT which has derivatives of all orders. It means it is smooth. Which has derivatives of all orders at T. Okay. So using the Taylor series, for this signal at T. So this is important. Otherwise, if you try to do it without saying that for this at T. So अगर आप इसको खुद करने जाएंगे, if you try to do it yourself, to just evaluate the Fourier series at T. Okay. We can express. So what we can do is we can express. So m of T plus Ts. So I am looking in the neighborhood of T. So I am writing the Fourier series at, the Taylor series at T, and I am finding the value in the neighborhood of T. Okay, neighborhood of T means capital of Ts should be nearby. So this can be written as m of T plus your T of S m dash T. This is the derivative at T plus Ts square by 2 factorial. This is the standard Taylor series formula. So I am not explicitly explaining how to write this Taylor series. This you can This you know already, and if you have forgotten it, you can just see it in the basic text on mathematics. Okay, but to be specific, I just written that it is at t. We are evaluating the series at t. So this will help you if you try to derive it yourself. So आपको t पे लिखना है फिर से plus ts cube by 3 factorial m the third derivative, and this goes on. Okay, as the Taylor series says, it goes on. Now this can be approximately written as m of t plus t of s m dash t for small ts. It means that if ts is small, then this ts square, ts cube, all these terms will start decreasing, because if small ts means generally it should be less than 1. So let us say 0.5, 0.2. So you can observe that once you basically they start squaring it, so the value starts decreasing. Okay, let us say 0.2 का square लिखेंगे तो 0.04 होगा. ओके, तो वो डिक्रीज हो गया. ऐसे ही आप 0.2 का क्यूब लिखेंगे तो वो फर्दर डिक्रीज हो जाएगा. सो दैट इज व्हाई वी आर सेइंग दैट फॉर सफिशिएंटली स्मॉल ts we can express m of t plus ts like this, approximate basically. You can say approximate. This is a very well term to use, that is approximate. Okay. So what does it show? So it shows that from the knowledge of the signal and its derivatives, at instant t, we can predict a future value at t plus ts. Okay. So this is what it shows. So this is the founding principle behind designing the predictor, which we would be studying. Okay. So let the kth sample of m of t. So earlier basically we were thinking of t being a continuous variable, so we wrote this down. Let us see what happens to the discrete case. See, this motivation is being given in B.P. Latin's book, and this is good because other textbooks would directly introduce the predictor to you. The problem is we can study the predictor directly, but as per my knowledge, you have not been introduced to random processes. So then doing autocorrelation functions and the derivation would be difficult for all of you to follow. So I am using this motivation, which I found is acceptable, you can say. Okay. K sample of mt be denoted as m of k, that is m of k ts is m of k. Okay. So basically you are replacing t by k ts. I must write like this. Okay. And m of kts plus minus ts is m of k plus minus. Okay, and so on. Okay. So I can approximate the derivative at k of ts. Now this is the standard derivative formula. Basically in this formula you tend ts to 0 to obtain the derivative. Let us say this is the derivation from first principles, whatever you call, or the derivative. That is, take two values which are nearby, subtract, divide by that interval, and let that interval tend to 0. This converges to the derivative of the sum. Okay. That is the standard. This is coming from the real analysis or from the basic calculus that you study. So we are not going into that. We are assuming that this approximation is good enough. Now, why all this is working? Because we have assumed our signal to be smoothly varying. and it is sufficiently correlated. So autocorrelation function is very wide, and PST also doesn't consist of basically high frequency terms. So उसी केस के लिए ये सब स्टडी जो है हमारी वैलिड है. This is not valid for other cases, okay? So, and sufficiently small ts. So remember the approximations we are using in order to make this explanation work, and this is true also in such scenario. Okay? So it means that m of k plus 1 can be approximated by m of k plus t of s into m of k minus m of k minus 1 divided by t of s. Okay, and this gives you what? This gives you that m of k plus 1 is equal to twice of m of k minus m of k minus 1. Okay. So this shows that we can find a crude prediction of the, why crude? Because this is sort of a hack, you can say, a crude prediction of the k plus 1th sample from the two previous samples. This is quite straightforward to follow. So now let us see that how can we use, now it is an obvious question, that can we add more samples? It means let us now start taking more terms in this series and we improve our approximation. So we will write it. So approximation may be improved if we add more terms. In the series. Now to determine, so this above thing is obvious that we can add more terms to improve our approximation. So determine the higher order derivatives. To determine the higher order derivatives in the series so we require more samples in the past. This is quite obvious. So m of k can approximate it by a1 m of k minus 1 plus a2. Let us say means you will get some coefficients a1, a2, they are some constants, m of k minus 2. And this goes on, suppose we are using n terms in the series, so a of capital N, m of k minus capital N. So it shows that with the help of a1, a2, an and n past samples of this sequence m of k, I can find the current sample m of k. Okay, or I can approximate it. This is a crude approximation because we have just used the Taylor series formulation for doing this. We may improve this, so that is what I am going to write. Now what it is, basically this is an equation. So this is the equation. This is the equation for nth order predictor. Okay. Larger n would result in better prediction in general. This is quite obvious in general. There might be few cases where this leads to some sort of basically if you are going through machine learning overfitting, or maybe there may be several other issues. We don't want to enter into those because linear regression and all these things is a separate area of study, and it has its own good, bad, whatever you call it. Okay? It means it has its own design criteria. So let me just draw this model, what basically where we have. So we have an input, we call this an input. So when I am writing m of k as the input, it means that it is a sort of a series which is coming in. So you first have a delay block. So delay by t of s. Then you further delay by t of s. And suppose this is your nth delay box. So delay by t of s only. But this is the nth block. This diagram you will find at several places, but for the sake of completion and for visualizing it aptly, I have just drawn it in the notes as well. Okay? I feel that if you visualize it at this point, this would be input A of n. You just have a summation block and you add and this is your output. Okay, so this is the input and this is the predicted value. Now this filter is called as a transversal filter. This is called as a transversal filter or a tapped delay line or a tapped delay line filter. Okay. Now, why it is called transversal? Because let us say you have n delay blocks and you are taking the values in between. So basically, from these two lines, you take one output. From these two lines, let us say between the blocks, you take one output. This is like this line acts like a transverse. Okay, this is a transverse line between the two. You can say this lines. So that's why you are taking samples in between, multiplying it by a, and you are adding. So this is a transversal filter tab delay line because this is a tab is TS. It means this is the gap delay, and it is creating some sort of a tabs. So this tab delay line, I think the terminology is more used in DSP. So if you are going through a course there, so you will see such filters there, or in signals and systems as well, where you study filter design. Okay. So it is a tab delay line. Multiple taps are there. Let us say here n taps are there or n delays are there. And this tap means that you are taking the output in between. So ऐसा नहीं आप एक सेंट्रल ब्लॉक भी बना सकते थे जिसके अंदर सीधा सिग्नल n से डिले हो जाता। नहीं, यहाँ पे आपने एक एक करके डिले किया है और उसके बीच में से आप आउटपुट ले रहे हैं. That's why the name comes transversal filter or tap delay. Okay. So here the tap gains. Here the tap gains. So this is called as a tap gains. ये एक टैप हो गया क्योंकि दोनों के बीच में से आप एक सिग्नल लेना चाहते हैं. डिले है फिर टैप है, डिले है फिर टैप है, डिले है फिर टैप है. So this is a tap delay. Okay. So here the tap gains are set equal to the prediction coefficients. Okay. So this is now one very important thing to say. Okay. Now you can observe in this that I am saying that there is an input m of k. Okay. So I am saying input is m of k and output is m cap k. But you realize that in this complete expression I am not using m of k. I am using m of k minus 1. You can say that m of k is being approximated with the help of previous n sample. So the current sample is not to be confused. Let us say if I say that I am just drawing it like a black box. Okay, tab TDL filter. I am writing. So this is called as TDL, or TV, or this is TV filter. So I am writing a TV. So or TV filter is there, and I write that this input is m of k and output is m of k cap. So you will get confused that if I already have m of k, then why are we predicting m of k? Okay. So the important thing to realize here is that this filter itself uses only previous n samples, okay, because of this delay block placed at the first point. So it should not be confused that if m of k is written here before the filter, so the prediction output will use the current value as well, because current value तो उसको predict करनी है, उसको वो यूज नहीं करेगा, बिकॉज लॉजिकल नहीं है वो चीज. जब आपके पास करंट वैल्यू है तो उसको आप प्रिडिक्ट क्यों करना चाहते हैं? ठीक है, तो इसके लिए आई एम राइटिंग वन मोर थिंग दैट इनपुट कंसिस्ट्स ऑफ, सो दिस इज इंपॉर्टेंट फॉर यू टू स्टडी एनी पॉसिबल diagram on DPCM from the textbook. Okay, so this is important. So I am just right because this otherwise it will lead to great confusion. So input consists of the previous sample. So that is why I will be drawing just a box also, basically around the text. So it consists of the previous samples. M of k minus 1, M of k minus 2, this goes on, M of k minus n. Although it is customary to say that the input, the input is mk. Okay, so this should be remembered. And the output is so this is customary to say. It means that we generally use this. So I am just, because it has been spread around the two pages, so I just draw half box. So for those who are studying through the notes, they can just read it with some attention. Why? Because this will help them understand the DPCM structures wherever they read from. Okay, so it's not at all compulsory to read from the textbooks I am giving or from the notes. You can have your own sources, and in those sources, if at all you encounter this issue that I am putting m of k as the input, I am putting m of k, or I am using m of k to predict m of k, that is a better thing to say that if I am using the current value to make its estimate, then this doesn't seem to be logical. See, why would we use the current value to predict its own? Then this is a problem which I don't think should have a solution, because if I have the sample m of k and I am using it to predict itself, then it's not a good thing. I should have m of k as the output only if I can use m of k. Okay. So m of k, the prediction should be based on the previous samples. I should not use the current sample, although I have it, but I should not use it to predict this value. Okay. So whatever way you understand it, this is logical as well. So this is what the basic predictor which we have introduced through the concept of Taylor series. Okay. So one thing to write that we have a very simple. So we have above a very simple. Procedure for predictor design. In a more sophisticated approach, so this is important. So I have not covered this. This you will find in most of the textbooks. Maybe I think Haken gives it. Haken, you can find this, that based on the autocorrelation function and differentiating the error, they obtain these prediction coefficients. But because I feel that we have not been introduced to random processes as of now, it's not good to do the derivation in the class, because I didn't simply have to say कि भाई ये आप RQ0 निकाल लीजिए, RQ1 है, RQ2 है, फिर differentiate करेंगे. So I assume it would go over the head. So that's why I have taken the Taylor series sort of formulation for this predictor. So in a more sophisticated approach, so I am just writing it down so that you know that there is a better way. So in a more sophisticated approach, MMSE, MMSE. So what is MMSE? Minimum mean square error. Basically, you take error, you square it, and find the mean, and then find the minimum over some parameter. That is the basic bifurcation of this word. Okay. For determining edges, okay, is used. Edges are the tab delay line coefficients, which comes out in terms of statistical correlation. So this is what I wanted to highlight, that because we have not been introduced to this concept, we are not doing that derivation. Anyways, that derivation is part of filter theory, adaptive filter theory. There is a branch of signal processing where we do these things extensively, okay, between various samples. Anyways, for those who know this, they can definitely read this derivation from the textbooks. You are most welcome, and if there is any issue, you can discuss it with me in a separate session. So DPCM, now we are finally coming to the DPCM structure, that is transmitter and receiver. Okay, I think in a few moments we will be done with DPCM. So we transmit in DPCM, we transmit D of k, which is equal to m of k minus the predicted value of k, m of k from the past samples, okay, m of, that is k cap, instead of m of k. So we will be transmitting D of k instead of m of k. And at the receiver, this is one point, at receiver, generate, so this is the principle for DPCM, generate m cap k from past sample values, okay. To which D of k is added to generate m k. This you can see from this. That is generate m cap k. If you generate m cap k from past samples, so you can just simply add it to dk to get m of k. To generate mk. Okay, this is simple logic. Now there is one issue with this. So let us write down the issue. Basically, there are two possibilities to do this. So these two possibilities are given in two possibilities. So below I am just writing one of the possibility which is mostly used, but for those who are interested, two possibilities are given in Couch's book. Okay, so you can just see that book. So it will give you two DPCM structures. So issue is, instead of past samples, there is an issue at the receiver. In the case you use this sort of a design. Okay, so instead of past samples, so receiver पे past samples available नहीं है, receiver पे उनके quantized values available. That is, so instead of past samples, m of k minus 1, m of k minus 2, is as well as dk. So as well as d of k, we have their quantized versions. This is the problem. Why? Because once you have d of k available with you, you are not going to transmit d of k as it is. You will be quantizing it and transmitting. Okay. Now the issue with quantizing is, you know that at the receiver, if I am given dqk, there is no means to find d of k. Means there is no way. This is a irreversible operation. So we have there quantized versions. That is we will see this d of k quantized value being available at the receiver, you know, but you will think that why I am saying that I have these quantized versions of mqk. Let us see. Once I will draw the transmitter receiver, you find it. So hence we cannot determine mqk. That is a problem. That if at all we need to use step 1, step 2, then we need to have d of k as well as the unquantized values or the original samples m of k minus 1, m of k minus 2, m of k minus n for this to give fruitful results. Okay, but it is an issue. So how to bypass that? Okay, first of all, let me just complete this and then. So we can determine MQ yeah, estimate of the. This is what I can best do. That I can use this mqk minus 1, mqk minus 2 and up to mqk minus n with d of qk to find mqk cap. मतलब हमने करंट सैंपल का जो m of k है उसका जो प्रिडिक्टेड वैल्यू और द क्वांटाइज्ड वैल्यू हम डिटरमाइन कर सकते हैं. Okay, so estimate of the quantized sample, estimate of the quantized sample mqk in terms of in terms of the quantization, in terms of the quantized samples so this is leading to this leads to an increase in error in construction. So first of all, you are predicting, then you are predicting the quantized values. So this will definitely increase this error. So let us see the strategy to work this out. See, after knowing the strategy, after I draw the transmitter and receiver, you will definitely get to know that what are we saying. Okay. So the strategy is that at the transmitter determine MQ cap. Determine MQ cap. Estimate of at the transmitter itself you do it. Estimate of MQ के इंस्टेड ऑफ लिमिट मतलब आप जो ट्रांसमीटर पे बनाएंगे इंस्टेड ऑफ ओके फ्रॉम द क्वांटाइज्ड सैंपल from quantized samples मीन्स जो रिसीवर पे मिलेगा हमें, अगर हम ट्रांसमीटर पे ही उसे जनरेट करके उससे अपना सिस्टम को डिजाइन करें तो रिसीवर पे एरर घट सकती है. दैट इज व्हाट इज द लॉजिक. एंड देन ट्रांसमिट द डिफरेंस m of k minus the predicted value of the quantized via PCM. So this is what is the logic. So let us see what is really happening. So now my error which I am getting is, which I need to transmit is, so m of k को लिया मैंने उसकी quantized version के predicted value निकाली. Okay, now what is why I am saying this value is predicted based on the quantized past samples. मतलब इसके basis पे जो value predict करूँगा, suppose इन n वैल्यूज के बेसिस पे मैंने जो वैल्यू प्रेडिक्ट करी उसको मैंने डिनोट किया m q k कैप से, बिकॉज इट हैज बीन प्रेडिक्टेड बेस्ड ऑन द प्रीवियस क्वांटाइज्ड सैंपल्स. एंड नाउ आई एम ट्रांसमिटिंग d of k. Now when I know if I need to transmit it via PCM, so I won't be transmitting it as it is. I need to quantize an input. So let us say that I am now transmitting dqk, which is d of k plus the quantization noise. Okay, that we know that I can definitely represent this by this. So dk में या तो आप plus noise add करेंगे या minus noise add करेंगे. It means it's not that it always has to be plus. This noise can take any possible value, plus or minus, because it has to be in between some. Let us say if dk is, if I am approximating it by the midpoint, so if dk is above this midpoint, so dq of k will be minus. And if it is below, so q of k will be plus, because this is, let us say, d of qk, this line. So either this can be the sample, this can be d of k, or this can be line above or below. Okay, so this q of k can be plus minus, whatever you call. No, it can be anything. So this is what is, this is quantization. Quantization. This we have seen when we were deriving the quantization noise. Okay, that we can represent this like that. Okay. Now, predictor output. Let us now first of all draw the transmitter, or let us first complete. So predicted output. Now, the predictor outputs. ये थोड़ा सा involved है DPCM का जो transmitter है. So what is happening is that I am just showing this to you today. I would say that why don't you go back, read it, because anyways it's exam time, and if there are doubts, or we can have a discussion again on Friday. We start our class with discussion on this. Okay. So predictor output is feedback. This feedback, it should be feedback, not feedback. It is to its input, so that predictor input mqk is. So let us say what I am doing is that I am having a feedback loop from the predictor. Let me just draw and see. Just give me 2 minutes. Let me write everything down, and then you can observe it. Which is equal to m of k minus d of k plus d of k, which is equal to m of k plus q. So let me first draw the structure. So what is the transmitter? So let us say this input m of k is coming. Okay. Let us say this is my d of k, the error. And as per my structure, I need to subtract the predicted value of the quantized. Okay. And because of being it a PCM, so I need to have a quantizer here. I need to transmit d of k, so first I need to quantize it, and let us say the quantized value is denoted by d of k, which have seen above should be d of k plus the quantization error. Okay. This goes to the channel. Means after encoding, so I have not added the encoding block here, you can just add it. There will be some processing, encoding has to be done, and then pulse shaping or whatever, this will be done. Now this error, what we do is, we have a summation block here. Okay. And the output of this summation block is fed back to the printer. Sorry, this acts as an input. Now we know that if at all your printer needs to work fine, or as per our logic, this should get m of q k as the input. This is a series, so I am see that is what I have written earlier, that m of q k as an input to printer means that for the current value of this k, printer will only use k minus 1, k minus 2, k minus 1. This should be known. So I need to have this because that is the logic, and this should give me this. That is predicted value of the current. ऐसा होना चाहिए. Okay, so this is a minus here, and this is a plus. Now the problem is that what should I add now to this? So I should do this. I should add one loop here. So basically what I am doing is that I am generating MQK by the addition of the past predicted series, and I am adding this DQK. So let us see what the analysis says. So analysis says that MQK as per my diagram is MQK cap, this is the MQK cap, plus DQK, which is this. Now MQK you can simply write, because our logic says that d of k is this, so you just put in here. Now this d of k and dqk you can realize from this that this is nothing but q of k. So you can say that mqk is this. So what we have really achieved? So what we have done is that instead of putting m of k directly as an input to the predictor, we have put in mqk as an input. Okay? And we are transmitting this difference, which is between mk and this. Now, there is one thing that mqk, you can say, is quantized value of mk. Okay? See, this is not the case, because this q of k is the quantization noise of d of k, okay, dqk. So you can say that this MQK is some sort of a quantized value, which is basically not generated because of M of k. This is the addition of M of k to Q of k, and Q of k being a quantization noise, so I just denote this as MQK. Okay? ऐसा नहीं है कि ये MK को quantize करके जो sample आ रहा है वो है, नहीं. ये वो sample है जिसके अंदर MK के अंदर हमने quantization noise of D add किया. So this you will realize if you work out this on your own. Okay. Let us see the receiver. The receiver is simple. Now you will see that because of the receiver we had to do all this hack. So that hack I am saying why, because this is an engineering hack, that the way to make the system more efficient and good. So this is a predictor. Okay, the same predictor you will be using at the receiver. Okay, this is this, and this is your input. Input is dq of k is the input which is coming. This is mq and k. Okay, and this is your output. Output is nothing but k. Okay. Yeah. So this is your this is the transmitter at the transmitter. So this is transmitter and this is your receiver. Let me write it down. So we are able they are able to receive the desired signal. M of k plus quantization noise d of k q of k. Now this is very, very important. I am writing in inverted commas so that you know it. Do not confuse that this MQK is the real quantization of MK. This is not real quantization of MK. This is because MK is being added with some quantization noise, which is the noise of or noise associated with the quantization operation of D of K. Okay, this you should know. So I am writing which is associated with difference signal associated with difference signal D of K, which is generally, this inverted commas are closed here, which is generally much smaller than MQK. तो इसका मतलब मीनिंग ये है कि अगर आपने m of k plus q of k में रिट्रीव कर लिया, बिकॉज mqk क्या है, m of k plus qk. Okay, so this is mqk, this mq cap k plus dq k, which is being done by the receiver as well. So ये आप रिसीवर का प्रिंटर है वो mq cap k प्रिंट करेगा और उसमें आप इनपुट को ऐड कर देंगे, वही आपका आउटपुट आ जाएगा, वही आउटपुट आप प्रिंटर को फीड कर देंगे, वही आपने यहाँ बनाया है सारा. तो अब आप स्कीम को ट्रांसमीटर रिसीवर को देखेंगे और तब आप ऊपर को स्टडी करेंगे. इफ यू नाउ गो बैक एंड स्टडी व्हाट वी हैव डिराइव्ड, यू विल रियलाइज दैट वी हैव बेसिकली अवॉइडेड अ लॉट ऑफ क्वांटाइजेशन एरर इन द सिस्टम, बिकॉज अब क्या आउटपुट आ रहा है, सिर्फ m of k plus d of k आ रहा है, सॉरी q of k which is very smaller than m, क्योंकि q of k वैसे भी क्वांटाइजेशन नॉइस था जो dk के साथ एसोसिएट होता है. Now finally what you will do is, so MQK आने के बाद आप इसको लो पास फिल्टर से पास कर देंगे ताकि आपका कंटिन्यूस टाइम सिंपल इज बैक. सो received samples MQK are decoded. So first you will decode, obviously, are decoded and passed through a low pass filter for deep conversion. Okay, so this is pretty much your DPCM transmitter. Okay, so this was what we wanted to do in DPCM. If there are any doubts, you can just go through the notes and the textbooks, whichever you are referring to, and we can discuss. We can just in the next class either we can discuss or we can discuss as per our convenience. It means you can just send me your doubt and I will think and respond. Okay. So time division multiplexing is the next topic, which is important for us to close module 1. Basically, we are running slightly late as compared to section B. Reason being that we have studied one or two things from different angles. Basically, I wanted to cover a few different angles to the sampling theorem. So this took 2 to 3 sessions. That's why we are somewhat lagging. But anyways, we should do things properly. So this is what I feel. So as per my conviction, I think we have discussed things at a satisfactory level. So even if we are late, it's fine. Now, what is this TDM? Okay. So I am just trying to explain the concept in let us say nutshell or graphically, or let us say intuitively. Rest of the things you can easily read from the textbook because we have had good background of sampling theorem and we have done things in a good manner up to now. So we can do it on our own as well. So suppose let us say there is a signal. So you have this signal and the sampling theorem has told you that you need to sample it at twice the maximum frequency content. So suppose this is a band limited to W hertz or B hertz, or W and B are interchangeably used in the textbooks. So let us say you collect the samples. Uniform sampling we are using. How about this question? This is 0 sample, then this is T of S. This is my sampling interval or time, you can say. This is 3T of S and this one. Now the problem is that if at the 0th instant I transmit it over the here, then I will transmit after. So let us say this is T equal to 0. Then after Ts second, I will transmit the second sample. Then after Ts, the third sample. I won't be transmitting as it is. Let us say some coding takes place or PCM takes place. You can say that let us say I'm doing it through the PCM. Okay. Let us say this is done through PCM. Okay. So the problem is that what is happening between 0 to Ts. So this channel is idle. Okay. Channel is not used. This is empty. It means इतना जो गैप है, लेट अस से टीएस जो था आपका 1 माइक्रोसेकंड था, तो 0 से लेके 1 माइक्रोसेकंड के बीच में आपका चैनल यूज नहीं हुआ। तो अब लॉजिक ये कहता है या एक जो वियर्ड थिंकिंग है कि क्या इसके बीच में हम किसी दूसरे यूजर की इंफॉर्मेशन भेज सकते हैं। तो द क्वेश्चन इज कैन वी ट्रांसमिट another or independent message in that. So the question is can we transmit independent. So I am not saying that कि हम सेम ही सीक्वेंस को लें और उसको उसके और सैंपल्स आगे वाले सैंपल्स को पीछे कर लें। इस तरीके के सिस्टम इंप्लीमेंट करने में मुश्किल होते हैं बिकॉज कॉजालिटी और सेवरल इश्यूज आ जाते हैं। तो लेट अस से हम इंडिपेंडेंट सोर्स ले लेते हैं दूसरा। सो कैन वी ट्रांसमिट इंडिपेंडेंट मैसेज सोर्स in between. So this is TDM, टाइम डिवीजन मल्टीप्लेक्सिंग कि आपने टाइम में सेवरल यूजर्स को मल्टीप्लेक्स कर दिया। 0 से टीएस के बीच में देखिए 0 पे एक सैंपल करंट सिग्नल का भेजा, फिर उसके बाद आपने और दूसरा सिग्नल से सैंपल भेज दी अंटिल टीएस कम्स। मतलब जब तक टीएस पहला 1 माइक्रोसेकंड पास नहीं हुआ तब तक आप दूसरे सिग्नल भेज रहे थे। जैसे ही 1 माइक्रोसेकंड आया और 1 माइक्रोसेकंड इलैप्स हुआ, आपने वापस इस सिग्नल को भेजा, फिर अगेन आपने दूसरों को भेजा, 2 टीएस पे आपने इसको भेजा, फिर आपने दूसरों को भेजा, फिर 3 टीएस पे इसको भेजा। बेसिकली दिस इज व्हाट इज टीडी। ये नटशेल में है टीडी। यही करना है हमें और इसी को हम उस एंगल से स्टडी करेंगे। तो दिस इज द थ्योरेटिकल, दिस इज द इंट्यूटिव फाउंडेशन ऑफ टाइम डिवीजन मल्टीप्लेक्सिंग। ओके, so let me write down a few things. So due to sampling theorem, so I am just writing it nicely. It means whatever I have explained above. So due to sampling theorem, transmission of information engages the communication channel, for only a fraction of the sampling interval. On a periodic basis. Okay, So this is what basically I have written, or what I have explained about time interval between time interval between adjacent samples is cleared for use by other independent message sources on a time shared basis. Okay, this is the complete thing. Means whatever I explained about, I have written it down. So this TDM is basically, so utilization of a common communication channel by multiple independent message sources without interference. Okay. So these terms are important, that it should not lead to interference. So this, if at all it is leading to interference, this is not a good system. This cannot be referred to as TDM. Why? Because TDM in itself implies that there should be error-free recovery or interference-free recovery at this. Now for motivation, let us just study one T1 system. Okay, I will introduce further concepts later. So let us first study the T1 system, okay, which is important for the perspective of covering module 1 completely. So T1 system was basically developed by Bell Labs 55 years ago, majorly used in North America and several other countries as well. Basically, they developed the telephone initially in several other countries. Where basically those who purchase the hardware from there, जैसे AT&T का hardware खरीदा तो उन सब जगहों पे ये आपका T1 system ही यूज होता है. इसमें क्या है? What do we do is, so 24 voice channels or a pair of twisted. So this is what is the basic system है. इट मींस दो लाइन वायर, मतलब आपके पास दो वायर है सिर्फ, इसके ऊपर आप 24 वॉइस चैनल्स यानी 24 टेलीफोन्स आपका सिग्नल आप एक साथ दे सकते हैं. तो दिस इज द रिवॉल्यूशन ब्रॉट बाय टीडीएम. यू नीड नॉट run 24 different wires to the exchange. You can simply take one cable, and on that one cable or one, let us say, twisted pair cable, you can have 24 voice channels. Okay, or a pair of twisted wires. Okay, pair of twisted. Now, for success, need to put. दिस इज इम्पोर्टेंट. इस तरीके के सिस्टम की सक्सेस के लिए, क्योंकि ये सिग्नल इतना वाइड बैंड हो जाएगा कि इसके ऊपर वायर के ऊपर काफी डिस्टॉर्शन है, तो कुछ दूरी पे आपको उस डिस्टॉर्शन को ठीक करना पड़ेगा, यानी रीजनरेट करना पड़ेगा फ्रेश पल्सेस. सो दैट इज व्हाट द डिजिटल कम्युनिकेशन enabled us to do. So need to put regenerated repeaters spaced at approximately 2 किलोमीटर. ओके, सो 2 किलोमीटर पे आपको एक बॉक्स लगाना पड़ेगा जिसके ऊपर वायर रहेगा और उस बॉक्स में सर्किटरी रहेगी जो कि इसको रीजनरेट करेगी. जैसे आप नोटिस करेंगे कि इवन नाउअडेज स्टिल दे आर प्रेवलेंट. So once you are roaming on roads, you will find that there are telephone boxes placed towards right or left side of the road, where you sometimes find a lineman doing some work there. Okay, so this is a sort of a regenerative repeater maybe at that point. So so let us see this. So I'm just describing the Stevens system so that over the next few days, those who are reading this course for exam, they can just go through this system because we have discussed it. So for in this system, what we do is we know that voice signal is limited to a band. Is limited means that is what they assume, and this is quite right, 300 hertz to 3100 kilohertz. Okay, that is what they assume. So we pass it with first pass. So first pass it through. First pass it through. This we have already known. This is called as the anti-aliasing filter. कि आप पहले ही pass कर दीजिए. Pass is through a low pass filter. That to a low pass filter with a cutoff frequency. Of about 3.1 kilohertz. That is what is the case. मतलब हमने इतना मान लिया कि 3100 hertz हो गई kilohertz. Either you write 3.1 kilohertz or 3131 hertz. This is not right. So this has to be. Basically, this should be a capital only, but sometimes we write small, sometimes we write capital. So, a frequency of about 3.1 kilohertz. Okay. Nyquist rate comes out to be. Nyquist rate is equal to 6.2 kilohertz. Why? Because twice of this. But the standard in systems, it is usually 8 kilohertz before. In this system, it's usually 8 kilohertz. 8 kilohertz is the standard sampling. Is the standard sampling rate. In telephone systems. So basically, this is in T1 system. In T1 system, you will use 8 kilohertz as the sampling rate for each of the voice channels. तो 24 voice channels हैं आपके पास और 8 kilohertz का sampling rate आपको हर voice channel के लिए use करना है. अब question ये है कि हम 24 को multiplex कैसे करें? Okay, so let us now do that. So each frame. So this is interesting. So each frame of multiplex signal occupies 1/8 kilohertz, which is equal to 125 microsecond. Now, what is the meaning of this? Let us say if I am saying कि 8 kilohertz is the sampling rate. Suppose this is voice channel 1. So if the first sample comes at, let us say, this point, and the second sample comes at this point, what is the sampling interval? This is simply 1/8, 125 microseconds. Why? Because we are collecting 8,000 samples per second. So 1/8000 is the sampling time. अब इसी के बीच में आपको 23 यूजर्स को डालना है. 23 users you have to put in between. Why? Because we saw in TDM कि आपको कैसे यूज करना है कि जीरो पे जब पहले सिग्नल का सैंपल आपने भेजा, उसके बाद बीच में आपके पास TS सेकंड्स का ही टाइम है जब आप बाकी इंडिपेंडेंट मैसेजेस को भेज सकते हैं. जैसे TS होगा, यानी कि इतना टाइम इलैप्स होगा, 1 माइक्रोसेकंड इलैप्स हो गया, तो आपको इस सिग्नल का, इस कंटीन्यूअस टाइम सिग्नल का नेक्स्ट सैंपल भेजना है. तो दैट इज व्हाट वी आर डूइंग हियर कि अगर वॉइस चैनल 1 का पहला सैंपल इस टाइम पे आया, तो दूसरा सैंपल 125 माइक्रोसेकंड का आएगा. के बाद आएगा। तो आपके पास 125 माइक्रोसेकंड्स ही हैं बाकी बचे हुए 23 यूजर्स को ट्रांसफर करना। तो अब वो कैसे करेंगे? अब हर यूजर जो है वो लेट अस से इट यूजेस so in this time it consists of let us say it should consist of और 125 माइक्रोसेकंड में ही आपको पूरे 24 यूजर्स को अकोमोडेट करना है। नटशेल में आप ये कह सकते हैं consists of 24 8-bit words. Why? Because and system uses 8-bit quantization. System uses 8-bit quantization. तो हर सैंपल 8 बिट, तो टोटल 24 यूजर और हर यूजर 8 बिट यूज करेगा, तो टोटल नंबर ऑफ बिट्स कितने हो गए? तो टोटल नंबर ऑफ बिट्स इज टोटल नंबर ऑफ बिट्स 24 into 8, that is simply 192. ओके, सो समझ लीजिए 125 माइक्रोसेकंड में 192 बिट्स ट्रांसफर करते हैं। ठीक है, अब इसके अंदर हम सिंक्रोनाइजेशन के लिए एक बिट और ऐड करेंगे। सो वी यूज वन मोर बिट, we use one more bit for synchronization purpose. So total number of bits is 192 plus 1, which is 193 bits. Let us check कि एक बिट को कितना टाइम मिलेगा। So let us say total कितने हैं हमारे पास 125 माइक्रोसेकंड, and we need 193 bits to occupy this. Okay, so you will find this out that per bit is 0.647 microseconds. So this is the time for allotted to a single bit. Okay, you can say per bit is required. And what is the transmission rate now? The transmission rate is only 1 upon 0.647 microsecond, which is 1.544 Mbps. So it means in this T1 system 1.544 megabits per second are transmitted over the two pair line. Okay, so जो कि अगर एक चैनल को आप भेजते तो कितना कम डेटा रेट आता, पर आपने सारे चैनल्स को मल्टीप्लेक्स किया तो बहुत हाई डेटा रेट आया। बट इसका एक कैच है, ये जो हाई डेटा रेट है दिस विल लीड टू अ ग्रेटर बैंडविड्थ कंजम्पशन, and this bandwidth consumption because your wires will definitely attenuate the signal at higher frequencies, you need to put regenerative repeaters. Okay, now because the cost of this system is somewhat, you can say, offset by the usage. A lot of people used to use telephones in their homes, and this was running on the wire line. Nowadays things are slightly different, but still wires are there, although at a lot of places optical fiber has replaced things, but you can still assume that this system is in use. But in earlier days, because of heavy usage, the cost was brought down, and placing regenerative repeaters was an easy task. So this sort of accommodation was okay. So we would discuss this thing in the next class. Okay.